Track it down. I'm like, okay, I was like, yeah, I'll go get that way. Yeah, I don't know, like okay, well, yeah, this is like red.
Okay, so oh, that's too loud. Okay, I'm sure people in the back row can hear me now. Okay, if you can't hear me, let me know and I can increase the volume. I think it's becoming too loud. Okay, good enough. Okay, so this is chapter 14, and we're going to learn about work done, principle of conservation of energy, and this is a way in which we can supplement what we learned previously. That is, sometimes it's easier to invoke these principles which we're going to talk in this chapter in order to solve problems. Given a problem which involves finding forces or motion, you can solve that with F equals ma, what we've done in chapter 13. However, what this is going to do is going to give you tricks on how to solve the problem by doing less work, okay? By using principle of work done, which is I'm going to teach today, and then conservation of energy, which is going to be taught the next class. So before we can use the principles, we need to know what it means to do work. Work done by a force is denoted by U. The formula for U is, well, differential first, is F dot dr, where F is the force, dr is the displacement, and the way you define this is the dot product between F and dr. If you remember the dot product, to take the dot product, you need to take the x components of F, multiply with the x component of dr, take the y component of F, multiply the y component of dr, and then sum it up. F is a vector, R is a vector, but U is a scalar, it's a number, okay? That's very important. You could also write it in this form. If you remember, recollect what the dot product does, it basically tells you the magnitude. You need to take the magnitude of F, magnitude of dr, and then take the cosine of the angle between the force and dr. Okay, and the angle theta is the angle made by the vector as shown. You cannot take the angle between, say, F is this way and R is that way. And theta is not the angle is shown, but it will be the angle. It will be an obtuse angle, not an acute angle like it's shown. Okay, it's important to have the arrows coming out from a common point. And then we want total work done, we just integrate that equation. Okay. Simple examples: if you are driving a car, when you apply, when you step on the gas, your force is in the forward direction, the direction of your velocity or displacement. In this case, the work done is positive. When you step on the brake, your force is going to be backwards, velocity is going to be the forward direction, or displacement in the forward direction, so the work done is going to be negative, right? And that correlates to that experience, notion of work done. So I'm going to define work done by two important quantities. One is gravity, other is spring, and then we'll talk about principle of work energy, and that's the principle we'll be using in this particular section to solve problems. So first, define work done by gravity. Okay, this is the work done when a mass moves under gravity. Minus mg y2 minus y1. So why is it negative? So we know that mg is the force and y2 minus y1 is the displacement. So final minus initial, this is displacement. The reason for the negative sign is because mg is downwards, like I've shown here, and y2 minus y1, which is the displacement, is upwards. Why is it upwards? Well, our convention is usually positive is upward. So as long as you have this convention, downwards is upwards is positive, you will have a negative sign. Okay, I would recommend you stick to the sign convention. Upwards is positive. So if your mass moves up, work done is negative. If it moves down, work done is positive. Okay, by this definition. Next is work done by a spring. And that is always negative. This is the initial displacement. This is the final displacement. Okay, why is it always negative? When you take a spring, you stretch it, the force is this way, right? But the spring has a tendency to compress back to its normal shape. So I'll correct that. So when you stretch a spring, the displacement is this way, but the restoring force on the spring is always opposing motion. So it's going to be that way. So displacement is to the right, my right, okay, your left, and restoring force is to the left or your right. And since the directions are opposite, the work done is negative. You can reverse the logic and say, well, what if you compress the spring? If you compress the spring, so this is the original length of the spring, you compress it, the displacement is to my left, your right, but the restoring force is always going to stretch the spring back to its original length. So force is that way. So displacement this way, force that way, the directions are opposite, work done is negative. So no matter what you do with the spring, stretch it or compress it, the force is always going to oppose displacement, hence it's negative. Okay, and finally, once we have these two, we've defined these two, now we are ready to apply, to define the principle of work energy. And this is the principle which we will use a lot, almost all the time in this section and following this to solve problems. So the principle of work energy states that the work done is the change in kinetic energy. So change in kinetic energy is half mv2 square. That's the final kinetic energy minus the initial kinetic energy. So if you move things around, we get half mv1 square plus the work done equals half mv2 square, or the initial kinetic energy plus the work done equals the final kinetic energy. Okay, so let's apply this principle. T1 plus U12 equals T2 and solve problems. Okay, and in order to find U12, you need to use one of those two expressions I wrote down earlier. Okay, design considerations for the bumper B on the 5 mg train, which is 5 times 10 raised to 6 grams, which is 5,000 kilograms, require the use of a non-linear spring having the load deflection characteristics shown in the graph. So this is how the spring behaves. Normally a spring is linear. That's what we normally are accustomed to, but this spring is non-linear. So it's a parabola and not a straight line. Select the proper value of K so that the maximum deflection of the spring is limited to 0.2 meters when the car traveling at 4 meters per second strikes the rigid stop. Neglect the mass of the car wheels. Okay, so the car is traveling at 4 meters per second, and then I don't know if you can see this, but right here there is a bumper, and that strikes the stop. And this bumper has the load characteristics shown there. And so what happens is, clearly when it strikes the stop, it's going to compress the spring, and eventually the car is going to come to a stop. So the bumper is absorbing the energy of the car, which is traveling at 4 meters per second. You're going to find K such that it will stop in 0.2 meters. So first of all, when you see any problem involving forces, I highly recommend you draw a free body diagram, because that's one way you can score partial points very easily. Okay, so a couple of things. What's the force due to gravity? It's mg. There is normal force, and then there is a force due to the spring, so let's call that Fs, and we assume that there's no friction between the rails and the wheels. Okay, so you do not have to show friction force unless it's specified. Just assume there's no friction force. Sometimes you have to the problem doesn't make sense unless you assume friction force, like we'll see later on in chapter 17 when there's something rolling. But if you're not given friction, just ignore it. So first of all, this is important. You do not need to use any concept from chapter 14 to solve this problem. You could totally solve this with what we've learned so far. We've learned F equals ma. This is a problem involving rectilinear motion in the xy coordinates. It's only in the x coordinates. So I would set up F equals ma, where F is that force K Fs, and then solve the problem without using work energy. So you do not need work energy to solve this. However, we'll solve it using work energy to show you how it works. But you're free to go home and try it out using equations of motion. That will give you the same answer. So let's use principle of work energy. which states that the initial kinetic energy plus U12 equals T2. The initial kinetic energy is that due to motion of the car, so it's half mv1 square. When you're finding U12, which is the work done by external forces, there is mg, there's n, and there's fs. Look at the free body diagram when you're writing this down. So those three forces, all of them are not doing work. So mg and n are not doing any work because mg, which is acting downwards, doesn't move the car up and down, nor is n doing any work. So the only force doing work in this case is fs, right? Because the motion is only in the x direction. So fs is the force which is acting to the left. Our convention is going to be positive is to the right, so I need to put a negative sign, and it's very important to put a negative sign, otherwise you'll get the answer wrong. Minus fs, and the displacement is to the right, so ds or dx if you like. I need to integrate from, let's see, it starts from 0, goes all the way to 0.2. Equals the final kinetic energy. So this is the energy when the car comes to rest, which is going to be 0. Okay, so let's write this down. Half mv1 square plus, well, this will be minus. Fs is given as ks square, which is really k. Okay, I should maybe write this as x because they chose the displacement to be s and not x. So ks square ds equals 0, 0 to 0.2. So half times the mass, which is 5,000, 4 square minus ks cube divided by 3, 0.2 and 0 for the limits. Okay, so that's a single equation and a single unknown, k. We can solve for it. Get k equals 15 times 10 raised to 6 Newton per meter square. Okay. So as I said, you can also do this with equations of motion. So if you write F equals ma, and this is only in the horizontal direction, F is minus ks square equals mass times acceleration, which is going to be, okay, what do I write? dv dt? If I do dv dt, then I will not be able to integrate this. So I need to write the other expression for a, which is v dv ds. Okay, so I need to integrate this from 0 to 0.2, and then initial velocity is 4, final velocity is 0. You can see that this comes out to be half m v square, 0 and 4, and you can actually compare this expression with this, maybe compare. If you compare it, you see that it's pretty much the same. So this is just saying that you could solve this problem using equations of motion. Principle of work energy, you need not use it. The difference you see is that in this case, I have to integrate both sides, ks square and mv dv ds. But in the first way, I just have to integrate ks square ds. In fact, if it was a linear spring, then I wouldn't have to do that integration. I would have just put half ks square minus half ks2 square minus s1 square. But this is a non-linear spring, So I need to carry out the integration. So this is showing you that you can do the same problem in two ways. So what we're going to learn in this chapter, whole chapter, are tricks to make your life easy, make it easy to compute the integration. Okay, any questions? Okay, if the motor exerts a constant force of 300 newtons on the cable, determine the speed of the 20 kg crate when it travels a distance of 10 meters up the plane starting from rest. The coefficient of kinetic friction between the crate and the plane is mu k equals 0.3. Okay, let me set this up for you, but I would want you to solve the problem eventually. So again, as I said, draw the free body diagram. Mg N, and then there's a force which comes from the cable. Is that all? Friction. I'm missing friction. So the block is moving upwards and friction always opposes motion. So friction is going to act downwards. Friction is mu k times n. So the displacement is upwards 10 meters. Okay, you can stick to that convention that upwards is positive. So principle of work energy, T1 plus U12 equals T2. Initial kinetic energy is 0. The final kinetic energy is half mv2 square. Okay, so I just want you to fill this part up. U12. Okay, there'll be a contribution due to, there are 4 forces, as you can see. Okay, we can resolve this force. Mg cosine theta and Mg sine theta. So there's going to be a contribution due to Mg sine theta. There's going to be a contribution due to mu kn, and there's going to be a contribution due to F. Okay, write those 3 things down and find V2. The V2 is an unknown. So can you solve for V2 and pull the answer? And you can take G as 9.81.
How much is the motor exerting?
300 newtons. Mu k is 0.3. M is 20 kgs. S is 10 meters. Okay, we'll stop. These people are not attending. Okay. Done, I'll stop. Okay, so I just wrote down the forces there. I just need to put the right sign into the displacement. The displacement is 10 meters. So let me write S. Okay, now mg sine theta acts downwards, but S is upwards, so that has to be a negative sign. Mu k mg cosine theta. Why I got that? Well, the normal force is mg cosine theta, right? That's using F equals ma in the vertical direction. So mu k mg is downwards, S is upwards, so it's negative. The force F acts upwards, S is upwards, so it's positive. Okay, let's put in the values. M is 29.81 sine of 30 degrees minus 0.3 29.81 cosine of 30 degrees plus the force 300, and we'll pull the S out, so 10 plus half mass, which is 20 times V2 squared. 12.28 meters per second. Let's close. The 8 kg block is moving with an initial speed of 5 meters per second. If the coefficient of kinetic friction between the block and the plane is 0.25, determine the compression in the spring when the block momentarily stops. So this is question.
I had a question on the previous.
Sure.
So for when it's an incline, don't we set the coordinate parallel to the incline?
Yes, that's how I said it actually. X and Y. That's why this is S equals 10. I did that, yeah. You're better off doing that. Okay, so the difference between this problem and the one which I solved earlier, the car, is that there's friction between the plane and the block. Okay, otherwise it's very similar, and that actually means that I need to account for the friction when I write the principle of work energy. So let me start off with the free body diagram. N mg, and I'm going to draw the free body diagram when the block is in contact with the spring. So when you compress the spring, it's going to try to stretch itself out, so the force is going to be to the left. So we call that Fs. Okay, so this is the free body diagram like it was for the car, except that I need to introduce the force due to friction. So let's write the principle of work energy. It states that T1 plus U12 equals T2. The initial kinetic energy is half mv1 square plus the work done. Now, again, there are four forces, as you can see in the figure. Two of those forces, normal force and mg, do no work because the block isn't moving up or down. It's only sliding in the horizontal direction. So the work done is due to the spring Fs. In this case, the spring is a linear spring, so I can just write minus half Ks. So let's say that the compression in the spring is x, so I can write kx square. It's negative because the work done by spring is negative. For S2, the final displacement, it is x square. The initial displacement is 1, 2 is in normal state, which is 0. It's unstretched. So the force due to the work done by friction is going to be, so here we can write Ff equals mu k times n, but n is mg. So I'm going to write mu k mg times the displacement is going to give me the work done. So the displacement is, well, friction acts for a distance of 2 meters, but it also acts for the displacement x because it's still sliding against the surface. So the work done is going to be force, which is mu k mg, times 2 plus x. Now the force is to the left, the displacement is to the right. In this case, the work done by friction is negative, equals 0. So half times 8 times 5 square minus half, k is 200, x is unknown, mu k is 0.25, m is 8, g is 9.81, 2 plus x equals 0. So if you look at that equation, the only unknown is x. It's a quadratic equation in x. You can solve that equation. I believe your calculators can do that. Solving for x gives x equals 0.6875 meters. Okay, as I said earlier, you could solve using equations of motion. Okay, this is a place where principle of work energy is advantageous over using equations of motion. That's because if you want to solve it using equations of motion, here's how you'll have to do it. You'll have to first solve for the velocity of the block when it reaches A. So you need to do F equals ma, where that force will only be the force due to friction. Solve for the velocity when the block reaches A. And then you'll have another set of equations. You have to use F equals ma again, but this time there'll be two forces, that due to the spring and the friction force. And then integrate from A all the way to full compression. So you'll have to solve this problem in parts if you're doing F equals ma, but if you do it using work energy, it's one single equation. Motion from A to full compression. So this is a place where, as I said, it's useful to use work energy. So it's a trick to make your life easy. Any questions? I highly recommend you try solving it the other way and see if you get the same answer as what I got using work energy. Should get the same answer. 3 feet down the plane starting from rest. 60. Neglect the mass of the coordinate pulleys. Okay, so A is moving down by 3 feet. Okay, let's set up the equations of motion. Before that, let's set up the free body diagram. Okay, let's draw a free body diagram for A. mg and mg cosine theta, mg sine theta, and then there's friction, so that's going to be mu k times n, then t. So this connects to the pulley, which is the same tension force. So that gets split into two. So T over 2, T divided by 2. And so the block B is going to be pulled up with a force of T divided by 2 because one of the strings wraps on the pulley which connects B. Let me write this as M. Okay, so when I solve this, what will happen is I'll have to, using principle of work energy, I'll have to write the work done by gravity when A moves down a distance and B moves up a certain distance. Now, the distance A moves down is not the same distance B moves up. So this involves me to do kinematics, which is something we learned in the chapter 12, right? If you have interconnected systems, how do we find the displacements and how they are related to each other? So we do this. So we have to sort of digress and find that relation before we can start applying the principle of work energy. So let's choose a coordinate because I want to describe the motion of B. Let me choose a coordinate over here to describe the motion of A. Okay, this is basically the position of A and B. I described it using those two variables. Now let me find a relation between XA and XB using the length of the cable. So length of the cable equals XB, okay, plus this part and this part. Now what you notice is that this part we're going to show as D does not change with time, so it's fixed. So the net distance is going to be XA plus XA minus D. So this distance is XA, but the other one, which I'm showing with a dark black line, is XA minus D. So XB plus 2XA minus D is the length. So then I differentiate with respect to time. L dot is 0 equals XB dot plus 2XA dot equals 0. So XB dot is minus 2XA dot. Okay. Now there's another way of writing this. It says that delta xb, and this was probably a confusion on Piazza. People ask this question. Xb dot is delta xb divided by delta t minus 2 delta xa divided by delta t, right? That's the definition of velocity. It's change in position divided by change in velocity, change in time. We can cancel this off, which is effectively saying that delta xb is minus 2 delta xa. So the displacement of b is equal to minus twice displacement of a. That's the relation I was after. Okay, now we are ready to use the principle of work energy. States that T1 plus U12 equals T2. Okay, everything starts from rest, so T1 is 0. Let's find the work done. Now, when you find the work done, you're going to write the work done due to the entire system, right? A and B. So the work done is MAG sine theta times delta XA. Now I'm going to assume that A goes down, right? My convention is XA is positive, the way I've shown, downward. So I'm going to put positive for this because MAG sine theta is downward, so is delta XA. Mu K, I think I got the friction incorrect. If it goes downwards, then friction will act. I need to correct this. Upwards. So friction is mu K mg mag cosine theta, and I would put delta XA with a negative sign. Okay, what else? mg cosine theta and n don't do no work. T does work, but what I'm going to do is I'm going to look at the system as a complete system where the two blocks are connected through the cables. So when that happens, the tensions do not figure in the equation. So I need to write the work done by mg, mbg, and I'm going to write delta xb positive, even though mb is going upwards. It is positive because my convention is mg is positive downwards and delta x is positive downwards. That's why my convention, I get a positive sign and not a negative sign. So that equals half MAVA square plus half, let me write it down as, I'm almost done, XA dot square plus half MBX dot B square. What needs to be done is I need to sub in for delta XA as minus 2 delta XB divided by 2, and XB dot as XA dot is minus XB dot divided by 2. Once I do that, I can solve for delta XA, and then I can solve for I know delta XA, delta XB. I just need to solve for V2 or VB or X dot B. I'll finish it up and post it.